first homework assignment was officially due half an hour ago, but it got extended until Saturday morning very early. You have 2 more days. So if you already did it, fine. Remember that you get extra credit if you do it 2 days before it's due. So any problems you've done so far, you're going to get your credit. Thursday, Friday. In fact, any that you do this afternoon also earn extra credit. There are a couple of people, well, I don't know. There were some people that had problems with the homework assignment. I want to cover a couple more things that you should know already, but it seems there are several people that don't. So where we left off last time, are there any questions or problems people are having? So, where we left off last time, remember, we want to find the area under some curve between, say, here, here, and, say, there. What we do is chop this up into a bunch of pieces, say, n pieces. So, I want to go from A, B, graph y equals f(x), and then in each piece, I choose some point, let's say the point on the right, and I call this point x1, I call this point x2, x3, this last point is xn, and then we just make little rectangles of that height, whatever the appropriate height is. These heights are negative, and I add them up. So that would be written as, well, the width of each rectangle is big, and the height of each rectangle is the function value there, and I just add them up. So for those of you that forgot, so this is the width, the height, location means, let me factor out the b minus a, so that must be right. 1, 2, right? So this gives me an approximation of the area. Now I take many rectangles, but their widths go to 0. So I take the limit of all of the rectangles that I have. I get lots of really skinny rectangles. And the limit here. And this is the area. So we have to prove that this is proven. I'm not proving this because supposedly you did this in your last class. This is defined to be the integral from a to b of f(x). This limit. So I do this little job where I add up all of these areas. And then I take the limit of the number of slices to infinity. Right? Is this new to anybody? Okay. So I got a number of questions about this. People were confused about this. So that's the definition of the integral. Of course, in practice, you rarely compute it that way unless you're using a computer or you don't know what else to do. But that's what we do. So let's take a specific example. So let's take the function y equals the natural log of x. And I want to write a limit which represents the integral from 1 to 3 of that. Okay, so this would be, this is going to be a Clipper question. So I'm going to give you some choices. You're going to tell me which one's right, and then I'll tell you whether you're right or not. So let's say the limit is n goes to infinity of the sum of 2 over n natural log of 1 plus x infinity from 2 over n natural log of y over n limit infinity to n infinity start this thing. Okay, so time to got up here. Everybody got their answer in? That's going to answer? Okay, we stop them. Okay, so very few people like answer 1. That's good because answer 1 is garbage. And very few people like answer D, which is also good because that's garbage. And so 35% of people think it's B, and the rest think it's 51%. So about half of you think this is the answer, and about a third of you think this is the answer, and the rest like A and D. So let's, I guess, do this problem. These two are very similar, except this one has a 1 here, and this one doesn't. Yeah? Sorry? They're all from I to n. But we take the limit as n goes to infinity. So in some sense it's from I to infinity, but if we put from I to infinity, then we're adding up big numbers. So we have to have the width shrink and the height vary. So that's why we have to go to n and stop. But then we take the limit as the number of slices we take goes to infinity. So in terms of the picture, it's kind of like this, except this picture is not the same function. Except as I take n bigger and bigger and bigger, these rectangles get really skinny. So my picture looks like, notice, like this. And so when n is really large, each of these things is a rectangle. From 1 to 2. Okay, so let me draw a slightly bigger rectangle. So here is a typical rectangle here at some xi. And this formula, which is written right on the board, tells me, oops, I'm going to 1 to 3. I'm sorry. At some point, my width is always b minus a over n. Well, all of these have a 2 over n, so that's cool. So 2 over n is fine, because this is b minus a. And then we have to figure out, well, how tall is this rectangle? So we have to think. We're going to chop up the region from 1 to 3 into a bunch of little pieces. And we're going to add them up. Well, how wide is any given piece? 2 over n. So the width here is 2 over n of each rectangle. If I move over n spaces, so for the first one, move over 1 space, how far have I gone when I start at 1 and I move over 1 step? I've gone 2 over n. So x1 is 1 plus 2 over n. Because I start here at 1, and I take a step of size 2 over n, and there I am. And x2 is wherever x1 was, plus 1 more rectangle, which is 1 plus 2 over n, plus 2 over n more, which is 1 plus 2 times 2 over n. And x3 is 1 plus 3 times 2 over n. And x22 is 1 plus 22 times 2 over n. So in general, xi is 1 plus I times 2 over n. And so if I go over here to xi, this is sitting here at 1 plus I times 2 over n, and the height is f of that value. So that means that I want f of 1 plus 2 over n times I. But f was the log. And then I want to take the limit. So this crazy looking notation is just a way for us to capture this idea. And we just have to be a little careful about chopping it up. There's a problem on the homework that I got about, yeah, go ahead. It's a number between 1 and n. So here, I is 1, and then it's 2, and then it's 3, and then it's 4, blah, 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 and then it's n. So it's representing which rectangle? Here I is 1, here I is 2, here I is 3. Since I don't know how many rectangles I have, I just have n. Maybe n is 100, maybe n is 1,000,000, maybe n is 5. I want to write the general rectangle, one of those dots. So I have to have it depend on I. Make sense? Now these limits are a pain in the neck to calculate. So we're not going to do it. Sorry, what was I saying? It's also possible to go the other way. You see a limit like this and you say, what area does this represent? That question doesn't actually have a single answer. Let me turn the question around. Suppose I have, I'm not going to ask this as a quick question. N goes to infinity, I 1, and so let's just leave it as a log. Let's actually do the same question. So I have this limit. Now we already know that this equals the integral from 1 to 3 of the log of x dx. Because we just did the problem the other way around. We already know that. But it also equals the integral from, say, 0 to 2 of the log of 1 plus x dx. It's the same. All I'm doing here is shifting my picture by 2. In this picture, I'm thinking Okay, here's the log of x, and I'm going from here to here. And I want that area. In this guy, instead I have a different function that's moved over by 1. The log of 1 plus x. This is the log of x. And instead I'm starting at 0 and going out to 2. Those are the same area, I've just shifted over a little bit. My notion of what x is has changed, but they're the same. And I can write infinitely many different variations on this theme, but they're all the same thing. So, if you have a question, write the integral, which this represents. That's not a reasonable question. That's like saying, write the name of a student in this class. There are lots of different names in this class. There's lots of different integrals that this represents. They all have the same value, but they vary. Okay? I don't want to, nor do I have time to, spend a lot more time on this. This is supposedly stuff you know, so I want to move on. As I said, so any questions on this? So as I said, doing these limits explicitly is tedious and nasty, so we don't usually do it. Just like in just like in taking derivatives, we don't usually take derivatives by the limit. We learn some rules, and then we use those rules, and away we go. But to get those rules, sometimes we have to keep going back to the definition. So, many of you, those of you, well, I guess all of you, have probably already seen something that turns this into something we can do a little easier. So here's a theorem which says that if f prime, let me use f and g because sometimes, so let's use g. If g prime of x equals f of x, so that means the derivative of g is f, then the integral from a to b of f of x dx is just g of b minus g of a. So that, in other words, if g is an antiderivative of f, then to do this integral, we just evaluate the antiderivative at each end. So, an easy example, we know that, let's say, derivative of x squared 2x, we know that the integral from, say, 1 to 3 of 2x dx is x squared evaluated from 1 to 3, which is 9 minus 1, which is 8. So, this should not be news to anybody, I hope. Is there anyone for whom this is news? Uh-oh. Maybe you don't want to. Maybe you're a smart guy. Well, okay. So this is actually half of something called the fundamental theorem of calculus. There's another half which I'll write in a minute. The reason it's a fundamental theorem, or the fundamental theorem, is it interrelates two very big things that you do in calculus. It says that to do integrals, you have to know about derivatives. You don't have to. Knowing about derivatives is good to know about integrals. Now, if you remember when I said last time that the theme in calculus is if we understand microscopic detail, then we understand macroscopic or full-size behavior, this is again a version of that, because the derivative here is microscopic information. It says, how is the function changing on a very small scale? And we can relate that to how the function changes on the big scale. So, and one thing that we do in this class is we prove stuff. No, we don't. I do. Why would this be true? So that's what it means in math, is to give a solid explanation, to prove something, you give a solid explanation of why it's true. I'm going to give a mostly solid explanation. It's maybe solid for you. I'm going to gloss over a number of the details that are mathematically subtle, but why would this be true? Well, we can do it in a fuzzy way. Well, maybe the fuzzy way is no help. Does anyone have a clue why this is true? Really? No? Oh, you do. Okay. Why? Well, that's what the theorem says. Integrals and derivatives are opposite. But why? Right? So, I mean, yes, it's true because integrals and derivatives are opposites. But it's like asking, why is the sky blue? Well, because it's this many angstroms. I don't know. Anyone know how many angstroms represent the wavelength of blue? So the sky is blue because the light that comes from the sky is blue. That's not an answer. I mean, it's an answer, but it doesn't tell you why. It just tells you it is because it is. So, okay. So has anyone seen a proof of this? Okay, you just forgot. It's okay. One whole person in this room has seen a proof of this in their life. 2 people, okay, good for you. All right, so why is this true? Well, let's think about what's going on with this integral. It's my function. You chop it up into a bunch of rectangles. And I evaluate, well, let's just give them names, x1, x2, xn. So let me not take the limit, let me just do it at n. So we know that this area well, let's start with the right. Let's start with the right side. So G, this is B, and this is A. And so G of B minus G of A, I can write it in a different way. This is G of xn, and I'm going to write G of x1 way over here. And then, just for fun, I'm going to subtract G of x, the one before, and add it back. I didn't get enough room. Maybe I should have done it the other way around. So this is 0, so nothing changed. And then I'm going to do it again. But I'm going to leave dots, because I don't want to do it again, and I still didn't leave enough room. So I'll put it down here. And then I'm going to get down to G of x2 plus G of x2, and then G of x1 plus G of x1. So nothing changed here. Just did that. And so those are certainly equal. Now, let's look at one of these little pieces. And there's a theorem that you probably forgot called the mean value theorem. Anyone remember the mean value theorem? Some of you, okay? I guess I'll do that back over here. get rid of that. Okay, so one of you that remembers the mean value theorem, do you remember it enough to tell me what it says? Yeah? Yeah, okay. You know it, but you don't. So, the mean value theorem, which you went over in your calculus class because it's important, but it seems stupid, says that if I have a nice function, I have a differentiable function, and this is, well, now it's g, but it doesn't matter. So let's call it, we'll call it g. So if g is a differentiable function, and it goes on some interval, then if I pick 2 points, let's call it xi and xi plus 1, so those are 2 points, then the slope from here to here the slope of the line through g of xi, so xi, g of xi, and the next guy. Those are my 2 points, which usually you call them A and B, but I already used A and B. And the slope of the line through there is the same as the derivative for some point in between. So there's some place, at least one place, this place, where the slope is the same. Another way to say this, you're driving your car in the New Jersey Turnpike. They hand you a ticket when you get off. You go 75 miles, and an hour later they hand you a ticket when you get on, and they say, you were speeding because you traveled 75 miles in 1 hour. You must have been going at least 75 miles an hour sometime. So the slope, the speed, is the same as the average speeds here. We don't know when it happened, but we know it happened sometime. Maybe you only speeded once, but you speeded. Okay, so that's what that says. Now, why is that useful here? That's useful here. I guess I want to write it differently. So that means g prime, let me call it I, because it sits between them. So that means that g prime of ci is the same as g so that's the same as that distance, right? This is the slope of the line, and there's the derivative. The slope of the line there is the same as the average of the 2 angles. Okay. Just for the hell of it, let's call this thing H. So that means that H times g prime of ci is this difference. Now let's look at this. I've got a whole bunch of things like that. So I have a whole bunch of these differences that I can just replace with derivatives. Right? This guy, since I'm going to take the limit, this guy is g prime of Cn times some number h, where h is the distance. And this guy is g prime. Actually, I don't need to replace them. Let me leave them over a. Sorry. I confused myself. Anyway, notice that if I divide everything by h, I get a bunch of different. Okay, so I subtract, I add and subtract, add and subtract, add and subtract. So this is what I started with, and this is what I started with. Oh yeah, thank you. Thank you. Okay. So now what have I got here? I've almost got what I want. Because now I have a bunch of derivatives sitting there. I'm trying to turn this into an image. So what is this? So I guess I'm going to write it over there. Sorry, I keep running back and forth. So that means that I've just shown that g of b minus g of a is going to be, well, that first thing over there is h times g prime of Cn. And the second thing is h times g prime of Cn minus 1. And the next one, h g prime of the next one. And so on. Why do I have g of x? So I have a sum of derivatives like this? Well, okay. Now I'm going to take the limit as h goes to 0. H is the width of the little rectangle. So when I take the limit as h goes to 0, this doesn't change. But as h goes to 0, the number of terms goes to infinity, so this is the same as n going to infinity. Well, what is this? This is exactly something that looks like, so h is the width of the rectangle, right? And g prime is the height with a different function. And I'm adding them up. I'm going to take the limit as the width goes to 0, or the number goes to infinity, and this is the integral. It's an x. So, it's magic. In other words, what's going on in terms of the picture, here, in terms of the picture, got this thing, and I replace each of these guys with the slope of someplace in between, and then I let them shrink to 0, so I'm adding up more and more and more and more slopes. I get the area. So it's magic. So this tells me that I can just do antiderivatives to do anything. Now the other way around of this, the other part of the fundamental theorem says that if I have an integral, now this is a little bit more brain-hurty, I suppose. Suppose that instead of just having, well, let me before I get to the other part. Instead of representing areas, definite areas, I want to think of functions defined by integrals. So if I have some function, here it is, and I start somewhere, here, I want every place I stop, like here, I get an area. Right? So if I move a little further, I get more area. So this is actually a function. I can define function to be the area. I can define some new function, which is the area underneath the curve. I go a certain distance, t, and then I stop. So an example of this, we know from physics that the derivative of position is velocity. The derivative of velocity is acceleration. You can think of this as being the graph of the velocity, and I want to know the position. If I drive my car at 60 miles an hour for 1 hour, I know the position is 60 miles away. If I drive my car at 60 miles an hour for 1 hour and 10 minutes, it's 66 miles away, and so on. The same business here. Defining a new function as the integral of the old one. So this is the integral from where I start, not to t, oops, yeah, t, of my old function. There. So I'm going to define the function. The variable here is not x, the variable is t. Where I stop, not what I did in between. Now this fundamental theorem tells me, well, that I can take the derivative of such a function. So the second part of the fundamental theorem says that if g of t is the integral from anywhere to t of f of t dt, then the derivative is just the function that I started. So these two together tell me that derivatives and integrals are inverses of one another. In terms of a picture, this is telling me that the rate of change of the area is just the derivative. I mean, just the function. Like, I want to look at area, I move a little bit, then the amount that this changed, the area here, here's my area, and I took some area, and now I moved the end a little bit. How much did this move? Well, just the height of the function, that's how much I moved it. The width of this is just the height of the function times how much it moved. Right? So those two things are related. This one is a little more subtle, but it's also extremely important. Let's try something on this. So let's use the same process. This should be easy. That can't be 2, so that should be x's. So A needs to be log of x log t minus log 3 e log 3 t log t. Do I have room for d? Can I put d up here? Sorry. our choices. You did both. So 70% of you got the right answer, and 30% of you were fooled. So this is not right, this is not right, this is not right. Also, this is not right. When you take the derivative, the endpoint dies. So it's just a law. Okay, let's change the problem a little bit. That's almost the same thing. So, not G, because I already used G. H. Thank you. These are X's. That was D math. So H prime T is A log T minus log 3 B log T squared C 2T log T squared D log T squared 3 Okay. Oops. Okay, so I'm stopping there. Stop. Okay, so 73% of you got it right, and 26 did not. So these are all stupid answers. That's a stupid answer. We're down to these two. Why is it this one? Right, we have to use the chain rule. So h of t is the same as g of t squared. And if we're taking the derivative of g of t squared, we need the chain rule. So h prime of t is g prime t squared times the derivative of t squared. So because of the chain rule, we need to do this. Okay, so that should be pretty straightforward. Away we go. Okay, this is Wednesday, right? Let's see, what else do I have to cover about? Okay, so maybe rather than doing a jillion examples like this, let me move on to the last review topic. I can use that one instead. So, I know I didn't do a ton of examples with decimal recitations before, so let me point out one last thing that you were supposed to know before you came to this class, and that's how to do easy integrals. So, of course, we can write integrals either as definite integrals, or we can define integrals, so as antiderivatives. Say I want to do let me do this one first. Suppose I want to do the integral from 1 to 3 of, say, x squared dx. So using the fundamental theorem, this tells me that I just need to find a function whose derivative is x squared. So a function whose derivative is x squared, well, the power here is 2. When I take the derivative, the power decreases by 1. So I would guess that I need a third power. But when I take the derivative of the third power, I get an extra factor of 3 that I don't like. Here there's no 3 sitting there. So I just divide everything by 3. And it's happy times. So this guy is just going to be, oops, what did I do wrong? No, that's right. So that means that this is x cubed over 3, and I plug in the values from 1 to 3. So this is 27 over 3 minus 1 over 3, which is 26 over 3. So that was pretty straightforward and pretty easy. Anybody confused by that at all? Okay. Suppose, though, I had something that looks slightly different. Say I have an integral from 0 to 2 of x plus 1 squared dx. Now I don't know off the top of my head a function whose derivative is x plus 1 squared, but it looks a lot like x squared. So what I do here is I say, gee, I wish this x plus 1 were really an x. Well, maybe instead of x, let's call it u. And then the differential here, when I change x a little bit, u changes by the same amount. And so that means that this becomes, and so also when x is 0, u is 1, and when x is 2, u is 3. So in terms of u, this becomes the integral I just did. Okay? No, from 1 to 3. So x goes from 0 to 2. When x is 0, u is 1, because u is x plus 1. And when x is 2, u is 3, because u is x plus 1. So when I write everything in terms of u, this is u equals 1, u equals 3, x equals 0, x equals 2. I want to emphasize, and I'll say more about this next time, it's important to write this dx and this du. These are akin to using the units in science. dx is like meters, and du is like feet. Now here, I've just shifted my feet by 1, so they're the same. But in other examples, which I don't have time to do today, but I will do on Friday, dx will vary. If you're having problems